Good day, guys. In this video, I'm going to give you a little bit of detail about diode. Okay, now this slide set is from Floyd's Principles of Electronic Circuit book. Uh, Okay, guys, you know diode is a package application of PN junction. So in background, what you see is a PN junction. You have already learned about basic operating principle of PN junction. So how we construct PN junction. Now, first figure here. Now that is example of forward bias situation of PN junction. We have current limiting resistor connected here. Now we connect positive terminal to anode of the diode and negative terminal to the cathode of diode. In that case, guys, because of the pressure that we create, so it create this depletion region thinner and it start to conduct. And second situation, it is a situation where diode is reverse bias and this depletion region is thicker. So because electron attacked by cathode and the uh, anode electrons is attracted to anode of the diode, and also holes attached to cathode of the diode. Likewise, we have thicker depletion region. So now in this situation, diode is not conducting. So this is the characteristic curve. If you look at the forward bias situation of a practical diode, you can see some curve like this. Now this voltage, it depends on the construct of diode. See, most of the silicon diode, this voltage is 0.7. Germanium, it is like 0.3. Now when till we apply this breakdown, the forward bias voltage, it is not conducting. So once it exceeds that voltage, it start to conduct like this. If you look at the reverse bias situation, so this is the breakdown voltage. When we exceed breakdown voltage, then only diode will conduct. We call this point its knee point. Now this is the full curve, reverse bias and forward bias. So these are some diode approximation, and we compare ideal model and the practical diode. So ideal model of diode, it is working as switch. So we should not see any forward bias voltage. Once we exceed like 0 voltage, we should see like the conducting. When we reverse bias it, like it should not conduct at all. So that is the ideal behavior. But practical diodes working different to this one. Now here you can see, so we always connected this resistor because we have current limiting diode. When we exceed that, we are burning the diode. So because of that, we have this current limiting diode. So in this situation, it is acting as a switch uh, when it is working in forward bias region, when it is working in reverse bias region. So it is like open switch. But practical diode, so working bit different to that one. So we have this forward bias voltage 0.7. When we exceed that one, then only it conducts. So now this figure indicate like forward bias voltage. So some equivalent circuit. If you look at this circuit, you can see till we exceed this voltage, it is not conducting. So now we can represent forward bias voltage like this. Okay, now when we look at this one, so if you apply Kirchhoff voltage law to this loop over here, you can see, so we have voltage rise, so that is V bias, and also voltage drop, that is this resistor voltage, and also we have this voltage VF, that is positive to negative voltage drop because of that negative. So then that should be equal to 0. Now VR limit voltage drop across this one, we can say I forward current multiplied by R limit. So when we substitute and simplify, we can say this forward bias current is equal V bias that means supply voltage minus V forward voltage for silicon diode, that is 0.7, divided by this limiting resistor, that is the slope. Okay, I hope that is clear to you. Okay, now so this slope, we see this slope, and also because in addition to this current limiting resistor, we have internal resistance in the diode as well. So this internal resistance we can represent like this. And also the reverse bias situation, we have this leakage current that is due to this connection in between these two terminals. So that is due to internal resistance of the diode. So then the forward voltage, actually it is not exactly 0.7. You will see slightly increased one. So forward current multiplied by this internal resistance, we get the exact forward voltage. And also forward current exact value is given by V bias minus 0.7 forward voltage divided by R limit plus R dash D. But this R dash D will be very small value. These are some practical instance of diodes. So you can see many diode, light emitting diode, IR, LED, and all these are application of diodes. And also here you can see different symbol that we use: Zener diode, Schottky diode, generic diode, and so on. So this, and also light emitting photodiode. So we have variety of symbol for each type of diode. Okay, thank you very much for watching this video.